Hi, welcome back. So we are getting down to the wire. Maybe 1, 2, 3 more lectures left, I think, for the entire school year. How about that, you guys? Nearing the end. So we're going to wrap up our air pollution unit lecture series today. So we have the Clean Air Act, which was put into action back in 1970, one of the first of our big 3 environmental legislation pieces, along with the Clean Water Act and the Endangered Species Act. All right. So much like the Clean Water Act, the Clean Air Act authorizes the Environmental Protection Agency to set limits on the amount of pollutants that are permitted from sources. Okay. And the Clean Air Act focuses primarily on 6 pollutants: lead, particulate matter, sulfur dioxide, carbon dioxide, nitrogen oxides, and ozone. Ozone, of course, being a secondary air pollutant, so really controlling things like nitrogen oxides also controls things like ozone. Lead, not so much an issue like it used to be. We used to have leaded gasoline, leaded paint, etc. No longer the case where we're adding lead because it's a pretty nasty thing to have airborne. And so that's what the Clean Air Act focuses on. Again, notice that there is no carbon dioxide. All right, and so the Paris Accords and stuff like that were designed to help us start managing the amount of CO2 we are producing, but it does not have the legal teeth that the Clean Air Act has. And in fact, the current administration is working very hard to allow us to back out of the Paris Accords, despite the fact that the rest of the developed world is bought in. All right, so how do we go about controlling air pollution? Okay, so again, what do we do to try to reduce these 6 pollutants? Okay, one of the things we do, particularly for particulate matter, is a lot of our exhaust stacks, or what they call smokestacks, are equipped with what are called electrostatic precipitators, right? And so what those are is there's an electrostatic charge, all right, and the particulate matter has a electrostatic attraction to those precipitators. All right, and so the particulate matter, as it is going up through the exhaust stacks, precipitator attracts those particles and allows them to settle out. So in this picture right here, you watch what happens. So these are the same 3 exhaust stacks. So without the electrostatic precipitator turned on, we run that electric charge through the exhaust stacks, and that is what the exhaust fumes look like. Now, there are still trace amounts of exhaust going out, and there's still gases coming out, but much, if not all, of the particulate matter is dealt with the installation of the electrostatic precipitator. It's pretty cool. Turned off, turned on, turned off, turned on. Pretty dramatic difference there. All right. Now, as far as dealing with some of the nasty gases like sulfur oxides, which lead to things like acid rain and so on, we installed scrubbers. Now, we did talk about scrubbers a bit way back in our unit in mining, also back when we talked about coal. All right. So the way that we go about trying to reduce, but not so much eliminate the amount of sulfur that escapes from things like power plants, etc., is we install scrubbers. And scrubbers use water and chemical additives to help reduce the sulfur that escapes with the gases, right? So, for example, if this was a coal-fired power plant, right, we'd have particulate matter dealt with by electrostatic precipitators. We'd have mercury, we'd have sulfur oxide and carbon dioxide, this whole concoction of nasty stuff. These scrubbers are pretty good at cleaning out darn near everything except, you guessed it, CO2 is going to come out with very little change as a result of those scrubbers. But it does deal with the stuff that is much more quickly nasty than CO2 would be. Okay? Now, controlling air pollution using vapor recovery. So, one of the class of compounds we haven't really talked about much yet are VOCs, which stands for volatile organic compounds. These are things that vaporize really quickly. So gasoline, for example, is a very volatile organic compound. So evaporates really quickly. So one of the things that they do when they come to fill up the tanks at the gas station using the trucks, right? As they pump new gas in, that empty tank, if it was empty, would be full of vapor. Right? So as the new gas comes in and starts to occupy that space, rather than just allowing that vapor to escape out, the same volume of vapor is recovered inside the truck that brought it. And then they can go and burn that off, for example, to reduce it to things like CO2, which would be much less harmful than the vapors from gasoline. All right. So these are just examples of some of the pollution controls, right? So we've got electrostatic precipitators, we've got scrubbers, we've got vapor recovery systems. But probably the most important way to deal with pollutants is what they would call source reduction. All right. So yes, we can deal with things like sulfur using scrubbers, but wouldn't it be great if the fuel we're using didn't put as much sulfur out to begin with? Okay. And that's that idea of source reduction. So burning low sulfur coal, low sulfur diesel fuel, etc. is going to help reduce the amount of work that our scrubbers have to do. Okay. And it's probably the best way to go about dealing with improving air quality, right? So reducing sulfur content in gasoline, all right? Requiring federal emissions standards, so reducing it at the source. Emissions testing for all vehicles, including diesel, which we do now in the U.S. Okay, so reducing it from the source. And then municipalities can even do things like synchronized stoplights, so we have fewer cars just idling in one space. Walla Walla stoplights, for example, are horrible. You can be sitting at a red light when there are no cars coming from any direction, yet I'm sitting there burning gasoline, idling my engine, when if the lights were synchronized or on motion detectors, I could scoot right along and have actually a fairly sizable impact on the air quality in downtown Walla Walla by just getting cars to move through as opposed to having them sit there and idle. Walla Walla actually is supposed to have, although it's not enforced, a no idle policy where people cannot just leave their cars running in park spaces. That improves air quality. So trying to reduce the source of the air pollution, again, plays a huge role in improving air quality. All right, so we're going to shift gears now. We're going to talk more detail about acid deposition, which would include acid rain. That's the more frequent way to put that. So we're going to talk quickly about the pH scale. You should all know at this point, right, just from being alive, right, and having a pulse, that a neutral pH is a pH of 7. Now, I'm not going to get in too much to what pH actually means. That's more of a chemistry concept. Probably not going to be something you see on the AP test. They will ask you about the pH scale, likely, though. Okay, so what we have to understand is we go above 7, we're a base. We go below 7, we're an acid. Right? And the further you go from that 7 mark, the more strong the base or more strong the acid is. All right? Now, natural rain. So when rain just falls through the atmosphere, okay, it does collect some carbon dioxide, which when it dissolves in the rainwater does produce a weak carbonic acid. So normal rainwater, right, is going to have a pH that's weakly acidic. Right? So between 5.6 and 5.8 would be rainwater. So natural rainwater, and there's nothing wrong with rainwater that has a pH of 5.6 to 5.8. It's very typical. Okay? So when we talk about acid rain, so technically all rain is acidic, but when we talk about acid rain, we're talking about rainwater whose pH has been nudged significantly lower than that normal level of 5.6 to 5.8. And again, that's going to vary from place to place, but that's your typical range. All right? So, what are the causes of acid rain? Well, things like sulfur dioxide and nitrogen dioxide, which are byproducts of combustion. So if you have sulfur-containing fuel, we're going to produce sulfur dioxides. Nitrogen oxides, as we've already talked about, are produced from reactions between oxygen and nitrogen at high temperatures, so internal combustion engine, power plants, etc. All right? Now, so these are our primary pollutants. Okay? And then their associated acids, so sulfuric acid, or sulfur dioxide would form sulfuric acid, which would be our secondary pollutant. Nitrogen dioxides would produce nitric acid, its secondary pollutant. Okay? Now, what we have to then consider is, well, what's the problem with acid deposition, right? Is this like so acidic that it falls on your skin and burns holes and causes your cars to rust quickly? Not so much that, okay? It's really more of a chronic issue as opposed to an acute issue, all right? But what do we get? So obviously, if you adjust the pH of a lake or stream, you could probably guess that that's going to cause issues with the natural balance of nutrients and what's soluble and what's not in water. So, for example, acid mine drainage is better able to dissolve things like lead and mercury and arsenic and cadmium, some toxic metals, right? It does cause thin-shelled eggs thin-shelled egg-producing birds to have lower fecundity, right? Which is reproductive success. And it also causes forest decline. And mostly, it's not because the acid directly poisons the forest per se. It's more that because the water is acidic, and again, the acidic water is often better able to dissolve certain things. The acidic water, as it percolates through the soil, it increases the rate of leaching. And of course, leaching, as we've talked about before, is the process by which, as water percolates through soil, it pulls nutrients with it. More acidic rainwater tends to increase the rate of leaching, and so we get really, really nutrient-poor soils where there's excessive amounts of acid rain. Okay, so again, acid rain is going to obviously affect our aquatic ecosystems, but it also makes it harder for some birds to reproduce because there's less protective shell, because shells will react with acids, and it also causes an increased rate of leaching of our soils. All right, moving around the world. Okay, so our developed world, so the United States and most of Western Europe and places like Japan, right? So we, along with our population stabilization, we've also seen environmental legislation accompany it. So if not the Clean Air Act and Clean Water Act, similar legislation in most of the developed world, right? So as you can imagine, we are seeing our worst air quality and water quality in our developing world, where the infrastructure and government legislation just hasn't gotten to that point yet to really diminish sources of those pollutants. All right? So, for example, if you look at the 5 worst cities in the world, China, Mexico, China, Iran, India, right? The developing world that's going through that demographic transition, mind you. They're seeing the worst air quality. There's in Shenyang, China, residents are only seeing actual sunlight a few days or a few weeks of the year because there's this constant, just gross haze of smog, etc. All right. Now, moving on to some earth science, right? Throwback to chapter 5 here. We have what's called the global distillation effect, right? So you might think, places like the far northern reaches of Alaska, for example, which have very, very few people and little to no direct pollution sources, right? Also tend to have surprisingly low air quality. And that is because atmospheric patterns transport our airborne pollutants long distances, and they tend to migrate poleward. Again, part of the reason Antarctica saw the ozone hole, right, is because we're taking those CFCs and transporting them polewardly, okay? And so the more volatile chemicals tend to travel farther and farther north, and that's what they call the global distillation effect. to increase our concentration of pollutants as we migrate toward the poles, despite the fact that very, very few sources, if any, are actually at the poles. All right, and then moving in to our final little piece here, which is on indoor air pollution. And again, I apologize, I'm going through a lot of material relatively quickly, but it's that time where we got to cram. All right, so indoor air pollution, what we have to understand about being inside is the volume of air is much less, right? So we get much less dilution of pollutants. So can be 5 to 100 times greater pollutant levels indoors than outdoors. So you're much more likely to experience carbon monoxide poisoning inside than outside, okay? And our most common pollutants indoors would be radon gas, which we'll talk about in more detail in just a second. And of course, depending on whether you have smokers in the house, but cigarette smoke is one of the more common indoor air pollutants. Carbon monoxide, nitrogen oxides, formaldehydes, volatile organic chemicals that come off your paint and your cleaners, all kinds of stuff. So the indoor air quality is often considerably worse than outside, with the exception of time periods where they have, the NOAA, or National Oceanic and Atmospheric Association, will sometimes put out a stagnant air warning. But for the most part, the air outside is going to be better and fewer or lower pollutant level than air inside. Okay. Now, the special case of radon. Okay, so radon is a gas, right? And it's a naturally occurring gas that is a byproduct of, well, it's actually not really a byproduct. It's a product of the decay of uranium, right? So as uranium radioactively decays over time, it goes through this whole chain and sequence of different elements it transmutates into, radon being one of them. And radon, being a gas, is considered an air pollutant. And so in basements, right, where you have a certain amount of uranium present in the sediments around, and uranium, while not enough to mine necessarily, is present fairly frequently in trace amounts, right? And so basements, because radon's an exceptionally dense gas for one, it tends to settle in basements, and because it's produced from uranium decay in the sediments, basements are particularly prone to radon, to infiltration of radon gas. You know, radon gas being an alpha emitter, and its ability to get into your lungs, it can be linked to things like lung cancers and so on, from exposure of your lung tissue to high energy radiation. Okay. And so improperly installed basements without the right kind of ventilation, etc., or sealing can see an increase in the amount of radon levels, which could be dangerous in certain cases. You guys may or may not remember, but a few years back, Blue Ridge Elementary was showing higher than normal levels of radon. And what you have to remember about Blue Ridge is it's a berm school. Most of it's underground because they built that hill. Now that does help insulate it, but it also increased the amount of radon that kids were exposed to. Now, the radon levels were still well below what would be considered dangerous, but they were above the federal standard for radon levels. So they had to go through and do a bunch of work to help remediate that issue. So no health effects are linked to that, by the way. It was just kind of we caught it and we got to deal with it. Okay, so this is one of those cases where federal standards are much, much stricter than they need to be to help, so we can always avoid the toxic levels. Okay, and that wraps up our chapter 20 notes. Again, I apologize, I went through lots of stuff fairly quickly, but you can pause and rewind, and if you come in tomorrow with some questions, that'd be great. I'll put together a little chart for us to kind of help organize our pollution classes and their effects and their sources, and whether they're primary or secondary pollutants and so on. All right? Enjoy the rest of your night.